Dear colleagues, let us talk about development of construction concept from an energy-efficient house to an energy plus one. Let me continue introducing my colleague Tetiana TKACHENKO, Doctor Habilitatus Professor, Head of the Department of Environmental Protection Technologies and Labor Safety in Kyiv National University of Construction and Architecture. She is a well-known professor and scientist in climate-resilient construction, circular economy, and renewable energy sources as the effective measures for climate change mitigation. The problem of energy efficiency is very strong. Mikita Moiseev, a Soviet mathematician and author of one of the first software for simulation ecological processes on Earth, said, "It's important to understand and feel that all life on Earth and the life of society itself for a long time took place only due to insignificant imbalance, almost an exact balance, between the energy that comes to Earth from space and the energy that is reflected by the planet. And a change in this imbalance, this relatively small value, threatens with very dangerous consequences. This creates a vicious circle of problems, leading to an avalanche of climate change. Therefore, increasing energy efficiency is a key task for achieving Sustainable Development Goals 13. Energy efficiency must be implemented comprehensively and account for energy generation, transmission, and consumption as a single system. Otherwise, the efficiency will be reduced. A comprehensive approach to energy efficiency in construction. The energy efficiency of a building begins with the choice of its shape. After all, heat loss occurs through the thermal envelope, wall, the floor, the first floor or basement, the roof or the attic floor. The most true criterion for optimality is the compactness ratio, the ratio of the area of the thermal envelope to the volume of the building. For buildings in which all horizontal sections have the same shape, the ratio of the perimeter to the area of the horizontal section can be used. The smaller this indicator, the less heat loss there will be in the building, which means that the building will be more energy efficient. In all cold countries, in accordance with this criterion for optimality, they tried to build houses of the simplest possible shape. In literature sources, there is a categorical statement that the most effective shape of a house is a hemisphere, followed by a cylinder, a square, a rectangle, a house with wings, and a house of a more complex shape. The statement is correct if there are no other restrictions. Hemispherical individual residential buildings are gaining popularity. For a residential and office building of a certain type of layout, the conditions of natural illumination limit the maximum distance from any internal point in the plan to the external walls. Under these conditions, several round or square building in plan will always have a larger area of the thermal envelope than one rectangular. An oval shape will be even better. At the same time, enlarging the building length decreases the perimeter per unit area. If the shape of a building with wings is so inefficient, as it's described, then castles and palaces would never be built in this form in our latitudes. Nevertheless, figures show the equivalence of the shape and the rectangular building by perimeter area and volume if the width and height of all parts of the building are the same. Similarly, turning a building at a street corner doesn't change these parameters. The criteria given don't take into account the influence of solar radiation of different wind conditions in different directions. Therefore, constructing the optimal geometric shape is a difficult task. Further, the choice of indoor environment parameters will have an impact on energy efficiency. This choice always faces a contradiction between comfort and energy consumption. Thermal comfort of a person corresponds to the case when he is able to dissipate all the heat produced as a result of metabolism without straining the thermoregulation system, and even more so without increasing or decreasing body temperature, hyper or hypothermia. The heat productivity of a person from metabolism depends on the activity. The possibility of heat transfer are determined by 5 microclimate parameters: air temperature, relative air humidity, air velocity, the level of velocity pulsation or turbulence intensity, and the average surface temperature or radiation temperature, and in addition by the thermal resistance of clothing. Thus, the energy efficiency of the building's microclimate formation strongly depends on non-building factors such as lifestyle, clothing, etc. Promoting an energy-efficient lifestyle is no less important than the energy efficiency of the building itself. For example, wearing warmer clothing during the cold season is more energy efficient than setting a higher air temperature. The next bastion of heat and cold preservation is the thermal envelopment. Undoubtedly, increasing the thermal resistance and increasing the tightness reduce the heat loss of building, which are the main directions of increasing energy efficiency. Nevertheless, thermal inertia has a double effect. It reduces the influence of external temperature fluctuations on the thermal regime of the room, which facilitate the work engineering systems. On the other hand, it creates a significant delay in the reaction of the room or to internal variable heat gains, and accordingly complicates the reaction of engineering systems to them. Further, the energy consumption of a building for the microclimate formation and meeting other needs is determined by its engineering systems. The two main requirements are minimal unproductive energy losses and effective automation of the response to changing indoor and outdoor conditions. Practice shows that thermal insulation of a house without heating automation increases energy consumption because people are forced to dispose of unnecessary heat by opening windows. Sealing a building allows controlling air exchange but doesn't eliminate its need. It's strictly forbidden to avoid sufficient ventilation in a sealed room. Otherwise, moisture, carbon dioxide, and pollutants from furniture and equipment will accumulate in the room. Increased humidity will lead to development of mold, which releases the world's strongest carcinogens, mycotoxins. As a result, a sick building syndrome occurs, manifested by symptoms of respiratory, cardiovascular, and other diseases that are not treatable with medication. It's treated only by ventilation. For energy-efficient ventilation, there must be utilization of exhaust air heat. Also, the utilization of heat from sewage and other possible sources is envisaged. To summarize the different ways of energy consumption of different energy types, the concept of primary energy, extracted energy before any conversion, is currently used. For different energy carriers, primary energy coefficients are taken into account, which consider its conversion and additional costs for obtaining the energy carrier. This approach is not ideal because it doesn't take into account the different potential of its different types. For example, electricity can be converted to heat up to 100%, and the efficiency of the reverse conversion is limited by the second law of thermodynamics. A more adequate method, exergy, takes into account only that parts of energy that can be obtained before achieving equilibrium with the environment. Despite better compliance with the physical content, this method still expects widespread use in the construction. To determine energy efficiency, the concept of energy efficiency classes was introduced. Back in the last century, the system of energy efficiency classes was calculated from A, the highest, to G, the lowest. The problem with the approach is that the development of technology, energy efficiency increases, and the classification system in this direction has a dead end. There are no letters before A. It's impossible to fix this for established association among consumers. Therefore, it's necessary to introduce classes A+, A++, and A+++, and then rewrite the entire classification system. So old class A equipment may correspond to modern class D. It should be understood that the energy efficiency class itself doesn't determine a specific value of energy consumption. It's a range of possible energy consumption relative to a certain baseline levels. Actual energy consumption is affected by operating modes, device settings, lifestyle, etc. It can only be stated that equipment of a higher class will consume less in the same conditions. The classification can be deeply revised. Let us show the example of Ukraine. Until July 2018, the specific energy consumption EP for heating, cooling, air conditioning, and hot water supply was related to the total heated area of residential buildings or the total heated volume of public buildings. Since July 2018, the class is determined by the specific energy consumption for heating and cooling or air conditioning only. One of the problems of the classification until July 2018 was the narrow range of Class C, which was later corrected. Thus, for the secondary market, we need to know the classification at the construction time in the corresponding country. Ukraine, thanks to the well-known specialist in the field of heating and ventilation, candidate of technical sciences, Associate Professor Viktor, introduced into the world practice of energy efficiency the requirement of classifying elements of engineering system and not only the buildings as a whole. At the same time, the energy efficiency class of a building cannot be higher than the lowest energy efficiency class of element of engineering system. Energy efficiency class A can only be achieved by combining all life support systems in a single automated system such as smart house. For example, where weather conditions change, the computer must assess whether it's effective to open window blinds and increase the power of the refrigeration machines to compensate for heat from solar radiation, or to close the blinds and use artificial illumination. An important point in centralized energy supply is the linking of the operating mode of energy generation, distribution, and consumption systems. For example, low power consumption leads to idling of turbines of electric generators and production of energy that isn't consumed, especially at nuclear power plants. This can be compensated by electric heat storage heating systems. Heating devices heat up at night and gradually give off heat during the day. These systems have low energy efficiency due to double energy conversion and unpredictability of energy demand next day, but they consume free energy, which would be dispersed into the environment in any case. Then use of electric accumulators will be more effective, but today such devices remain environmentally hazardous during disposal. All of the above only consider operational energy costs. In the previous century, energy costs for construction itself were not considered. Today, the concept of embodied energy and accordingly embodied carbon is used, that is, energy costs and released carbon in all processes, from raw material extraction to the disposal of building materials. At the same time, all technological processes, transportation, installation, etc., are taken into account. Specialized databases can be created for various building materials and products. And now let us talk about transition from energy efficient house to energy plus. Construction with near zero energy consumption has become a logical continuation of energy efficient construction and has become possible with the development of renewable energy and the use of secondary sources. It has become possible to achieve a level of energy demand that can be covered by secondary resources, heat of exhaust air, wastewater, and renewable energy, solar, wind. From 2021, all new buildings in the EU must be built with at least near zero energy consumption. The development of European standard in the field of energy efficiency is shown in infographics. The requirement of near zero energy buildings are highly dependent on the climate conditions. The EU requirements are different for different regions and different types of buildings. One of the major problems with most renewable sources is their intermittent nature. This problem is solved in three ways. The first way is accumulation. It's associated with the following problems. For thermal energy, a large volume of heat storage. For electricity, the environmental hazard of batteries, or in the case of using water electrolysis, the explosion hazard and low efficiency. For mechanical energy, large flywheel sizes and the danger of their self-destruction. Online systems with the ability to sell excess energy, electricity, heat and or cold at a green tariff and purchase energy from the grid in case of shortage are associated with the following problems. The need to adapt centralized energy supply sources and networks to unstable renewable energy inputs, problems with tariff policies, possible fraud, etc. Coordination of energy consumption and supply regimes is the third way. For example, washing and dishwashing with available renewable energy requires having a sufficient amount of dishes and clothes in case of a prolonged energy shortage, as well as an adequate response to a possible sudden interruption of energy supply, sudden cloudiness, cessation of wind, or sudden storm. Heating hot water requires a sufficient volume of water heater and suffers from problems in the long-term absence of renewable energy. Mobile device charging can only be arranged for devices with a suitable usage pattern, such as flashlights or laptop tablets that are used personally during non-working hours. For phones or laptops that are used continuously, this can be arranged from wind energy available at night, but not from solar energy available during the working hours. Reducing energy consumption and increasing the generation of energy from renewable sources allows achieving a complete balance between consumption and the generation of energy. In such houses, not only the roof used to convert solar energy, but also translucent fences, blinds, walls, etc. Such houses are called houses with zero energy consumption. It would be correct to call such houses energy independent, but if they don't use the capabilities of online systems, then a disruption in the system will lead to idle energy generation and the lack of life support during a shortage of renewable energy. Their specific energy requirements must correspond to the available generation capabilities, which are in the vast majority lower than the standards for near zero energy buildings. Further increase in generation leads to its exceeding of energy needs. Such houses are called active or energy plus. This allows receiving not only comfort but also income. Let us talk about cautions. Near zero energy and energy plus buildings rarely pay for themselves in a reasonable amount of time. They are built primarily because of social responsibility, to achieve a certain level of prestige, and to achieve energy independence in order to avoid problems in the event of centralized power supply failure. They often generate significant income and pay for themselves quickly, but not directly. They serve as advertising for the products or services provided there. When building houses with energy generation, it's important to remember that generators have a limited service life. For example, solar panels degrade, that is, they constantly reduce the efficiency of converting solar energy into electricity. It's believed that when the efficiency drops by half, the panel's life is finished. But everyone set this threshold independently. It's important to remember that the environmental impact of disposing of the panel as waste is not so good. Modern electric batteries wear out with a gradual decrease in capacity and a possible sudden complete loss of it at a certain point in time. The chemicals in such batteries are dangerous for the environment and cannot be recycled. Today, new storage technologies are being actively developed, for example, graphene batteries. But until environmentally safe electricity storage technologies appear, the use of existing technology must be responsible. And now let us conclude. Energy efficiency is a necessary condition for the survival of humanity. Increased energy consumption leads to launch of a vicious circle, deepening climate change and increasing energy needs. Energy efficiency in construction should be approached comprehensively, taking into account both construction and non-construction factors. In particular, the key condition is the promotion of an appropriate lifestyle. Thermal comfort is determined by the ability to dissipate the heat produced as a result of metabolism without straining the thermoregulation system. The energy efficiency of building is ensured by the correct shape, thermal insulation shell, and engineering system. Energy efficiency should be considered in the complex of energy production, supply, consumption. For example, less energy efficient solutions such as heat storage heating, which allow using energy during a period of energy consumption drop, increase the efficiency of such a complex as a whole. Buildings are classified according to energy efficiency classes from A highest to G lowest. At the same time, the classification is periodically revised. If previously only energy consumption during the operation of building was considered, today the concept of embodied energy and embodied carbon is used. Energy consumed and carbon released throughout the entire life cycle of building materials and products from raw material extraction to waste disposal. Increasing energy efficiency and energy production from renewable sources allows for the construction of buildings with close to zero energy consumption, and energy plus. The main cautions are long payback and need to solve the problem of unstable energy supply from renewable sources and the limited service life of generators and batteries. Thank you for your attention.